Alright, so this is a very, very special day. We're starting a new chapter, chapter 4, which is a chapter on areas. It's a huge, huge chapter because we talked about this before. We talked about it, the first week of class. Let me see if I can pull this stuff up. Jot down your memory. We said calculus has two huge ideas in mind. It has the idea of finding slopes and the idea of areas, and we try to explain why areas are everywhere, and that's why it's such a crucial question. Every time humans have multiplied two quantities to yield another quantity that's meaningful, you've got an area problem. And every area problem is also a slope problem in disguise, and vice versa. That was all fine, but the problem with these areas is that aren't all little squares or triangles. Some of them can get crazy like that. By the way, last section was monumental. We did one of these areas that are supposed to be only for gods, the ones with a bunch of curves, with the antiderivative of the velocity function and the position function and all that, with the mean value theorem. That was huge, huge. We got a little taste of it, and this whole chapter is devoted to that issue, the issue of finding areas. Of course, the problem was, or the strategy was, this huge, big, and super bold idea, the idea that we would take the area under there and break it up into infinite little pieces that are pretty close to zero, but there's infinite many of them. And you have this dilemma of adding infinite many incredibly small pieces. That's what you call riding the bull, baby. When you can play with that stuff, you're playing with some big boy toys or big girl toys, whatever your perspective is. And also when you're dividing these, finding these tangent slopes involve finding ratios of things like, let me see, things like f of x minus f of y all over x minus y. It's pretty close to 0 over 0, and we did that a lot. We find all sorts of things like that. They were called derivatives, functions that give you the tangent slope. Did all that for many, many chapters. All right, we are now ready to focus on that problem, the problem of areas. Okay, we're done with the slopes for now. We did a whole chapter on that. We're ready for areas. We're ready for this stuff. Well, not really. We're almost ready for it. What I want to do this first section is not jump right into that, but I want to take one or two sections just to review our adding properties, because we're going to be adding infinite many things that are infinitely small, and it makes no sense to do that if we don't even know how to add 5 or 10 things that are not even small, that are just normal size. So before we jump in there, we got to take a couple sections to review our sums. That, my friends, that's the name of the game today. How does that sound to you? Okay, this whole chapter is about areas, and areas under some function, but we start off easy. We start off just with a little review of sums. Okay? Does that sound good? This one's for all you Brazilians. You guys know how to live life, man. Music. Timeless ideas. Espresso. Yeah. See, what does that do to your brain when you listen to stuff like that? Alright, so here's a little review for sums. First thing we want to review is the famous notation. This notation is this sigma, which is a Greek version of capital S for sum. And this is standard notation. Everybody knows it, well known. And it goes like this. You've got some function here. Usually people call it a with a little n, or a of n like this, which means some function with n's in it. And then you have the n is the index, and at the bottom of the sum you have the starting point. For example, I can start off with 1, and at the top I have the stopping point, so maybe I stop at 3. This one would mean you have your function here, you're plugging 1 wherever you see n, so you have a of 1, then you plug in 2, a of 2, then you plug in 3, and the 3 over here tells you stop. Stop when you get to 3. That's what that means. Okay? As a quick and silly example here, what if it changed it up a little bit and went from 7 to 10? Another little example, what would that mean? Well, that would mean I plug in 7, so I get the 7th term of the sequence, or whatever the output is when I plug in 7 in for n into this formula. And then I would plug in 8, and then I would plug in 9, and then I would plug in 10 into my A recipe. That's not the kind of teacher I am, so I'll erase that and make it better. So plus a of 10, that would be the last one. Okay, that's for generic form an. Let's actually try a couple examples maybe. What if that formula was n over n plus 1? I've got a summation here. This is this should be n. Let's make this n. This index should match that one, otherwise this is a constant, it doesn't change. But I meant to have n there, and I did it on purpose just to show you that the index has to match. So this tells me where to start. Start at 2, so I would get 2 over 2 plus 1. That's it for my first term. Then I would plug in 3. So I get 3 over 3 plus 1. Then I would plug in 4. 4 there, 4 there. I would get 4 over 4 plus 1. Then I would plug in 5. 5 there over 5 there. And then I would stop, because this tells me stop when you get to 5. And then I could add those up if I had nothing better to do. But I do have something better to do. So forget it. I'm not going to do that. Anyways, you can do that. That's grunt work. That's what that sum means. Okay, I'll do it. 2 over 3 plus 3 over 4 plus 4 over 5 plus 5 over 6. That's 2. I got to get a common denominator. 5. You see, I told you it's grunt work. No. Your mind and my mind are way, way too precious to waste on grunt work. Forget about that one. Next example. What if you had a simple one? What if you had the index is n, but you've got no index here? Huh? What are you going to do then? Well, same thing, same principle applies. Wherever you see n, you plug in 1. Well, I don't see n, so I'm done plugging. N is equal to 2, I would get another 4. N is equal to 3, I would get another 4. N is equal to 4, I'd get another 4. N is equal to 5, I would get another one. So I'd get a grand total of 4 plus 4 plus 4 plus 4. Okay, I'll do this grunt work. 5 times 4. That would be the grand total. That's too easy. Let's do another one. Oh yeah, I wanted to note that sometimes it's very common to not write them as a function, rather than writing these as a of n using the function notation. Often books or people or myself will write it as a with a little subscript n. These two mean the same thing. It means some sequence or some formula that has n's in it, and for every single n you get an output, and usually n represents a natural number. So this one, again, you would plug in 1 wherever you see n. So I see it there, so I plug it there. Then I plug in 2, so I would get a2. Then I would get a3. Then I would get a4. Then I would get a5. Then I would stop. That's what that means. And if I knew the formulas for each of these, I could go ahead and plug them in there. Let's do this one. Oh, see here that I made the indexes match. So the k is the one that's changing. So this would be 3 times 1 plus 3 times 2 plus 3 times 3 plus 3 times 4, and the 4 up here tells me stop when you get to 4. So obediently I stop there. And that would be 3 times 1 plus 2 plus 3 plus 4, whatever that is. Who cares? Okay? This lecture is going to go by quick. Alright? Salute. Timeless ideas. Actually, they're not that timeless. They're actually ideas from algebra. They're just review. But the reason I'm doing them here is because we got some big time stuff coming up tomorrow, or the next lecture, where we actually add infinite many things that are infinitely small, and we can't be adding those things if we don't even know how to add the simple ones. So that's why this review is really important. But it's not. I wouldn't call them exactly big time ideas. But the music is still good, and the espresso. All right. What we want to do is start studying some simple properties. Okay. Simple properties. These will help us in the future. Here's a famous simple property. If you've got something like this, summation, and in this case you've got two different formulas. You got a formula there, an. We'll call that a separate formula, and this one a separate formula, bn. And you went in and you did it the normal way. You'd get, well, that's equal to a1 plus b1, because the recipe says, hey, wherever you see n, you plug in 1. I see n there, I plug in 1. I see n there, I plug in 1. And then I do the same thing but plugging in 2. So I'd get a2 plus b2. That means 2 placing to the a formula plus 2 placing to the b formula. Then I would do the same thing for 3. I would get a3 plus b3. And then I would do the same thing for 4. a4 plus b4. And then here's something interesting. We're going to design or derive a special property of this, or special case of this property. If these are real numbers, I can shuffle them around and gather all the a's together. So I have a1 plus a2 plus a3 plus a4 plus b1 plus b2 plus b3 plus b4. And now I can change this back to my sigma notation. This is sigma of all the an's, starting with the first one and stopping at the fourth one. And this is all the sum of all the bn's as n runs from 1 to 4. And what I've done is I've shown that the sum of the an plus bn as n goes from 1 to 4, this sum can actually be distributed into that one and distributed that one, and you make two separate sums. This is similar to what we did for limits. Limits can be distributed when each one was existing as finite. By the way, the same applies here. When each one exists and is finite, you can distribute this sigma and break it up into two smaller pieces. That will become very, very handy in many occasions. Super important property. I would call it distribute the sigma. You could distribute this to each square. And of course, if you had 3 or 4, or if this was minus instead of plus, same thing. You could still distribute it as long as each one exists and is finite, like these finite sums. We can play that game. Okay, that was a pretty simple property, right? Let's try another one. Simple property. This one would say, hey, if I've got 7 times an, and I'm going through use the definition, I'll get 7 times a1 plus 7 times a2 plus 7 times a3 plus 7 times a4, and then I'd stop there at 4. But something interesting happens here. You see the 7 there, and a 7 there, and a 7 there, and a 7 there. I could actually factor that out and just have a1 plus a2 plus a3 plus a4. And this suggests another very interesting property. This suggests that I could change this back to my sigma notation, an's, as n runs from 1 to 4. And look what I've done. I've taken 7an as n goes from 1 to 4. By the way, this wouldn't make a difference. If it was 1 to 1,000, the same concept would still apply. What's interesting here, the important thing to note is this 7 right here. It comes through the sigma as in osmosis, and it comes out, you could pull it out. It's called pulling the constant. Again, something similar to what we did for derivatives, something similar to what we did for limits. And we do it again for sigmas. You can pull out the constant because all it is just a distributive law. Capiche? Super famous. Okay? Pulling the constant. And this other one, super famous, distributing the sigma. But wait, there's more. These next couple properties, I got 2 more for today, and then it'll be an easy day today. I got 2 more properties. This next property deals with the index. It says, hey, this index starts at 7 and stops at 10. The reason these next properties are important is because often we will have actual formulas to add these things with a lot of efficiency. These are very, very nice formulas, but the formulas work only when you start at 1 or maybe at 0. And a lot of those formulas don't particularly do so well when you start at 7. But the next couple properties tell you how to shift the index, how to get it to start at 1. Let me tell you this one, for example. This idea says, you know what? What if I had, what if I forget about that? Just forget about that for a second. Let's put that off to the side here. There it is, off to the side. Whoa. Off to the side. Let's delete that. Here's an idea. Timeless idea. What if I had added up all the numbers? This time I'm going to do subscript. A1 plus A2 plus A3 plus A4 plus A5 plus A6 plus A7 plus A8 plus A9 plus, I can't believe I get paid to do this, A10. What would be another way to write that? Another way to write that would be say, hey, you know what? This one I can break it up and say this one is just the A's from 1 to 6 plus the ones from 7 to 10. And that's the same thing as adding all of the ones from 1 to 10. What that suggests is that all my ANs starting from 1 to 6 added to all my ANs starting from starting from 7 to 10, right? Starting from 7th one to the 10th one. Again, that's not the kind of teacher I am, so I fix it. Make it look nice. N is equal to 7. Yeah? That's equal to the whole thing. That would be the sum of all of the ANs starting with 1, stop at 10. Stop me if I'm lying. You ain't lying, teacher. That's it. Right? The sum of all the ANs from 1 to 6 plus the ones from 7 to 10 is the same thing as the ones from 1 to 10. But, wait, there's more. I could take this one and solve for it. After all, notice the connection here. This is the one I was looking for, the one from 7 to 10. This is the one from 7 to 10. I could solve for this one by moving this to the other side. And I get this very nice property. Whoa. There's a very nice property that says that all my ANs starting from 7 to 10 is the same thing as all my ANs starting from 1 and going all the way to 10. But wait a minute, that's not good. Not from 1 to 10. I got to subtract the other ones that I added extra. All the ANs starting from 1 stop at 6. Or said differently, I take this guy right here and just move it over to the other side and it becomes negative. Okay, I'll say it two different ways. I could solve for this one by just moving this one to the other side. Done. Or I could look at it this way. The sum of all the ANs from 7 to 10 is the same thing as the sum of all the ANs from 1 to 10, but then subtract the extra ones you added, the ones from 1 to 6. Okay, very, very nice property. But it's deep. You might think it's just silly, but no, it's super important. And the reason it's super important is because, look at it. There will be many cases where we don't have a good recipe for a sum starting at 7, but we have recipes when they start at 1, and this one starts at 1, and this one starts at 1. Piece of cake, not a piece of cake. So we turn something that's not a piece of cake into something that's the difference of a couple pieces of cake. I told you. You see why they pay me? That's why this is an important property. And it has to do with shifting the index. Okay? But wait, there's more. I don't know why that one's there. Simple property. Oh, that one's just a shift. That's a review of the other one. We can review that one or not. You could distribute it as n goes from 1 to 4 of n squares plus the summation as n goes from 1 to 4 of the 3 n's. And then you could do summation of all the n squares as n goes from 1 to 4. Plus, you could pull the constant 3, summation of all the n's as n goes from 1 to 4. And that would be equal to 1 square plus 2 square plus 3 square plus 4 square. That's that piece, plus 3, parentheses, 1 plus 2 plus 3 plus 4. And you can do that if you need practice. If you're a beginner, you probably should do that. If you're not a beginner, it's probably grunt work, and your mind is too precious to do that, so it's up to you. Oh, but I wanted to explore the same property over here. This is the one that's shifting index. This is saying, the way we wrote it here, what this is saying is that if I have some formula here, starting from 7 to 10, I can use the same formula from 1 to 10, but subtract the ones from 1 to 6. That would mean that this one is equal to 7, that one is equal to, let's go with white, just like white. That would mean that it's all the squares starting from 1 to 10. And you say, wait a minute, I was supposed to start at 7, not at 1. Oh, no problem, we can fix that. Minus all the n squares as n goes from 1 to 6. What that means is that 7 squared plus 8 squared plus 9 squared plus 10 squared is the same thing as 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared plus 8 squared plus 9 squared plus 10 squared. That's that minus 1 square minus 2 square minus 3 square minus 4 square minus 5 square minus 6 square minus all these squares. And of course that leaves exactly the same. Told you. See that? This piece right here would be exactly the same. That's just a way to really illustrate the property. Maybe that was overkill. But wait, there's more. I got a different idea. Here's a second property, a second way of shifting the index. Different than the one I just told you. The idea I just told you was, hey, go all the way from 1 to 10 and subtract the ones from 1 to 6. Here's a different way to look at it. I could subtract to that one. Subtract 6. If I subtract 6, what would happen? Well, I would start off at 1, and I want to start off at 1 often. Well, that's easy. Just subtract from 6 and subtract 6. Subtract 6 from there and 6 from there. That would go from 1 to 4. But whatever you subtracted here, you have to make it up over there. So I would have to add it here, n plus 6 square. So short, so simple, so beautiful. Yeah, this is another way to shift the index. And you say, whoa, that was too fast. Well, you can always rewind if you want. But let me try to explain it a different way. Over here, if you were to go through the plugging in of these numbers in there and figuring out, writing out the sum the long way, the very first one you have to plug in would be 7. So you would plug in 7 there, and what would you get? You get 7 square, right? And what would the next one be? You would plug in 8, you'd get 8 square. Okay, let's check on that side. If I plug in the very first one, n is equal to 1, I would get 1 plus 6. That's 7 squared. Exactly the same as I got over there, 7 squared. For the next one, I would plug in n equals 2. That would be 2 plus 6 is 8, 8 squared. That's the same thing as the next one, the second one up here. The second one would have been 8, 8 square. The very last one is 10 square. The very last one here is 4 plus 6 square. Same thing. I told you, it's brilliant. A way of shifting the index to get you started off at 1. Or wherever you want. You could subtract it. You could have subtracted whatever you want. Whatever you subtract from these ones, subtract, I don't care if you subtract 100 from here, add it to this one. Or if you add 100 to these ones, subtract it from here. Do the opposite that you do here. Look at this. Whatever you do here, you do the opposite here. Whatever you do here, you do the opposite there. If you add 2 here, you subtract 2 here. If you add 6 here, you subtract 6 here. Subtract 6 here, you add 6 here. Told you. That's why they pay me.